Hi folks, welcome to chapter 2. In this chapter we are going to be looking at units of measurement. We are going to be looking at the SI units. We are going to be looking at significant figures. And we are going to be looking at conversions, that is how we can convert from one system of units to the other system of units. So let's look at large and small measurements. Now, scientists and chemists often deal with very big and very small numbers. For example, the distance from the Earth to the Sun is 149,600,000,000 meters. And there is a hydrothermal worm, that is a worm that lives in water, and it has a width of 0.005 meters. Now, with these large and very small numbers, how do we convey the information in a way that is easily understandable? That takes us to what is called scientific notation. With scientific notation, we have what is called a coefficient, we have what is called a multiplier, and we have an exponent. So now, the coefficient is a number that is always between 1 and 9. For example, in this our example here, the coefficient here is 2.14. So the coefficient is always between 1 and 9. And here we have the multiplier. This is the multiplier. And we have an exponent, which is the power to which that number is raised. Now, let's see how we can express that exponential notation. For exponential notation, we are going to be looking at the situation where we are starting with the raised to the power, the exponent, okay, the multiplier and the exponent. Here we have 10 raised to the power 0. Anything that is raised to the power 0 is equal to 1. Now we are going to look at the positive exponent and the negative exponent. So let's start with the positive exponent. So 10 raised to the power 1, it will be equal to 10. So if we have 10 raised to the power 1 is equal to 10. Now, if we have 10 raised to the power 2 is the same like 10 times 10, okay, which is 100. So if we have 10 raised to the power 3 is the same like 10 times 10 times 10, which is equal to 1,000. All right. Now, let's look at negative exponents. So if we have 10 raised to the power minus 1, that is the same like 1 divided by 10 and is equal to 0.1. So if you have 10 raised to the power minus 2 is the same as 1 divided by 10 times 10, okay, which is 0.01. And if we have 10 raised to the power minus 3 is the same as 1 divided by 10 times 10 times 10, which is 0.001. Now, let's look at examples of exponential notation. We are going to start with 0. So 5.1 times 10 raised to the power 0. Remember, I've said anything raised to the power 0 is 1. So 5.1 times 10 raised to the power 0 is going to give us 5.1. Okay. Now, let's look at a second example. We're going to look at 5.1 times 10 raised to the power 1. That is going to give us 51. Okay, because 10 raised to the power 1 is 10 times 5.1, that's going to give us 51. Now let's look at the third example here, that is 5.1 times 10 raised to the power 2. That is going to give us 510. Okay, take care of the way we are doing these multiplications. Now these are the positive exponents. Let's look at the negative. So let's look at the third one here, 5.1 times 10 to the power 3. That is the same like 5,100. Now, we see here the powers. Anything raised to the power 0 is 1. And as the powers are increasing, we are moving one place to the right. So, let's look at the negative exponent. So if we have 5.1 times 10 raised to the power minus 1, we are going to have 0.51. We are moving to the left, so we are moving to this direction. So when we multiply using the positive exponent, we are moving towards this direction. So that is exactly what we are doing with the negative exponent. We have values that are less than 1. So we are moving to the left. So if we have 5.1 times 10 raised to the power minus 2, it means that we are going to move 2 decimal places to the left, which is going to give us 0.051. So if we have 5.1 times 10 raised to the power minus 3, we are going to move 3 places. 1, 2, 3 places. So that is going to give us 0.0051. So let's see how we can move from standard to scientific notation. Because what we have right here, for example, in the first case here, 2.5 million, that's 2,500,000. That is standard notation. Now let's see how we can move from standard notation to scientific notation. With scientific notation, we have said we have a coefficient, we have a multiplier, and we have an exponent. Now with this first example, the decimal point is considered to be here. So if we have to move it to scientific notation, what we are going to do is we have to move the decimal. Remember, the coefficient must be between 1 and 9. So we are moving to the left. So this is going to be 1. We're moving from here. That's 1, 2, 3, 4, 5, 6. So we have 2.5 times 10 raised to the power 6. Okay, so that is exactly what we have. So we are moving 6 places to the left. So that gives us 2.5 times 10 to the power 6 liters. The units are very important because anything without a unit, it doesn't really make sense. Looking at the second example here, we have 137 billion joules. So that is a unit of energy. So how do we move from this standard notation to scientific notation? We are at this point. So we are going to be moving to the left. And how many places are we going to move to the left? We are going to move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we've moved 11 digits. So the answer is going to be 1.37 times 10 raised to the power 11 joules. Now, that is for big numbers. Now let's look at the case of small numbers here. For example, we have 0.000000142 gram. So how do we move? Now, if we are moving from left to right, in this case, because our coefficient must be between 1 and 10, we will see that the value is going to be negative for the multiplier, that the coefficient is going to be negative. So let's see. We're moving 1, 2, 3, 4, 5, 6, 7. Okay, so we move 7 digits to the right. And the answer is going to be 1.42 times 10 minus 7 grams. Okay, so you have to be careful to remember when it is positive and when it is negative. When you are dealing with a very large number and you want to convert it, remember it's going to be positive. When you are dealing with a very small number and you are moving to the right, the power, the exponent is going to be negative. Let's look at the last example here, 0.000326 centimeters. So since our coefficient must be between 1 and 10, so it means that we are going to have 3.26 here. So how many places are we going to move? We're going to move 1, 2, 3, 4. So we've moved 4 places. So that's giving us 3.26 times 10 raised to the power minus 4 centimeters. So that is how you convert from standard notation to scientific notation and vice versa. Now let's see how we can move from a scientific notation to standard notation. For example, here we have 1.528 times 10 raised to the power 5 kilograms. So when you see this, you know that the value that we are going to have is going to be big. So we are going to be moving to the right. Okay, so whatever we have here, we are going to be moving 5 places to the right in this first example. So let's see. Now that's going to be 1.528. So that's the 1.528 that we have, and we are going to move 5 places, that is 10 raised to the power 5. So that's giving 1, 2, 3, 4, 5 places. So that gives us a final answer of 152,800 kilograms. Okay, so that is how you move from scientific notation to standard notation. Now let's look at the second example here. The second example, we have 1.64 times 10 raised to the power 7 liters. So we are going to be moving 7 places to the right from where the decimal is here. We are going to be moving 7 places to the right. So let's see. That is going, we have 1.64 and we are moving 7 places. So that gives us 16,400,000 liters. That is for positive numbers. Now let's see what happens with the negative numbers. With the negative numbers, we are going to be moving to the left. Okay, it's the opposite. So we are having a number that is small. So we are going to be moving to the left. For example, in this case, the 1.35 that we have, we are going to be moving 5 places to the left, not to the right. In this case, 5 places to the left. So let's see how to do that. 1, 2, 3, 4, 5. So we fill it up with zeros, and that gives us a value of 0.0000135 meters. Same thing for 8.28 times 10 to the power minus 3 grams. So let's first of all write out our 8.28. Now we are moving it 3 places, and that is to the left. So if we move 3 places, that is going to give us 2 zeros. So that is 0.00828 grams. So now you can conveniently move any big number that you have to standard notation or to scientific notation, depending on whatever question you've been asked. Now let's see how we can deal with calculations that involve scientific notation. Now in this case, let's look at multiplication. So how do we deal with calculations that involve multiplication? When we are dealing with multiplication, what we do is that we are going to multiply these coefficients and we add the powers. We are just going to add these powers. So that is what we are going to do. We just add the exponents. Okay, so we are going to multiply 3.1 times 2. That is going to give us 6.2, and what we are going to do next is that we are going to add the exponents. So we are going to add 4 plus 2, that gives us 6. So if we multiply 3.1 times 2.0, that gives us 6.2. Then for the exponents, now we are going to add 4 plus 2, that gives us 6. So that is going to be 6.2 times 10 raised to the power 6. So that is what you do with multiplication. Now let's look at the case of division. When we are carrying out division, we are going to divide the numerator by the denominator, and we are going to subtract the exponents. So for division, we subtract the exponent, and for multiplication, we add the exponents. So we are going to divide the coefficients. 8.4 divided by 2.0, and then for the coefficients, for the exponents, we are going to subtract 7 minus 3. So that is going to give us 4.2 if we divide the coefficients. And now if we subtract the exponents, that is 7 minus 3, that is going to be 4.2 times 10 raised to the power 4. So that is how you do the calculations involving division. Now let's look at this other example. 2.5 times 10 raised to the power 4 plus 6.0 times 10 raised to the power 8. So we are going to multiply the coefficients, and then we are going to add the exponents. So 2.5 times 6, that's going to give us 15. And then if we add the exponents, 10 raised to the power 4 plus 10 raised to the power 8 here. That's going to give us 10 raised to the power 12. Remember, we said in scientific notation, our answer must be between 1 and 10. So here we have 15. So it is not in scientific notation. We have to move again from this position. We are going to move one place to the left. And if we are moving to the left, it means that we are going to be adding the power. So that is what happens. So we move one digit and the power is increasing by 1 because we've moved one place. So that is going to give us 1.5 times 10 raised to the power 13. Now, we are going to be dealing with a lot of calculations in this course, and you need to master how to use your calculator. So this is the TI-36X solar, but what we are using, as I gave in the syllabus, we're using like the TI-30XA. That is simpler to be used, and that is what I master. So I can help you out if you use the TI-30XA. Now let's see how we can use the exponent using this calculator. So most of these calculators, you will see the exponent here, where you see this yellow right here. That is where you have to press the exponent. For example, if you were asked to press 4.5 exponent 16, you are going to click 4.5 in your calculator, then you press the EE, then you press the 16. So if it was 4.5 exponential negative 16, you are going to press 4.5, then you press the exponent, you press 16 and minus. Okay, so that is how you use the calculator. In other calculators, you are going to see just an E for the exponent. Others you will see EE, others you will see an E, and for others you will see EXP. So that stands for the exponent, which is a number raised to a certain power. So that power will be determined in the question that you are given. So that is x raised to the power. So the power here, you have to fill in whatever power you have. Now let's look at an example here. Like we have 1.53 times 10 raised to the power 16. So this is what you are going to punch in your calculator. You are going to punch 1.53, then you write, you punch the EE, then 16. So that is 1.53 exponential 16. So that is how you write that out. Now let's move to measurements. We've looked at this scientific notation, standard notation. Let's look at now measurements and units. So here we have a tape that we can use in measuring length. We also have a graduated cylinder here that we can use in measuring volumes. And everything that we are measuring, for it to have sense, we need to add units to it. So we are looking at measurements and units now. So units of measurement are quantities with accepted values that can be communicated between people. Okay, let's look at the measurement and units here. Like we are looking at a car here that is traveling. You want to measure the speed. Maybe it is traveling at 65 miles per hour. So you are looking at the units here. Maybe you are looking at this food right here, and you have to look at the calories, you have to look at the fats, you have to look at the cholesterol. Everything there has to be given units. If they are not given units, it will not make sense. So for example, let's say maybe you were downloading files in your computer and it was downloading at 373 kilobytes per second. So that makes more meaning when the units are given. Or maybe you were working in your farm and you were trying to fertilize your farm and you were using 170 pounds per acre of ammonia to do the fertilization, to put the fertilizer, sorry. So now let's look at the units. We are going to look at two types of units here, which are the English and the metric units. Okay, for the measurement of length, we are going to see the metric unit and we are going to see the English unit. America, the United States, uses the English units, And in the scientific world, we use the metric units. So let's look at, for example, the measurement of length. In the metric unit, which is what you are going to be seeing in this course, we are talking about meters. And in the English unit, you will see foot or you will see mile. Now, what is the relationship between meters and feet? We know that 1 meter is equal to 3.280 feet, and 1 kilometer is equal to 0.621 miles. Now, if we want to measure mass or weight, in the metric unit, it is measured in kilograms, and in the English unit, we are talking about pound. And the relationship between kilograms and pound is that 1 kilogram is equal to 2.204 pound. And if we are looking at volume, in the metric unit, we are talking about liters. And if we are talking about the English system, we will be talking about gallons. And what is the relationship between gallons and liters? 1 liter is equal to 0.264 gallons. So these relationships here, they are very important because we call them conversion factors. And that is what we are going to be using in conversions to convert from one system of units to the other. Now, let's look at what we call fundamental units and derived units. We have 7 fundamental units where any other units that you would see in science are derived from these 7 fundamental units. And these 7 fundamental units are mass, which has the measurement of mass, which is in kilograms, even though we are going to be dealing with grams and milligrams when we are dealing with very small masses. The measurement of length, we are going to be looking at meters. We can also look at millimeters, and we're gonna see so many of those. Now, when we are looking at time, for time, the time is in seconds, which is the unit. We are also going to be seeing time in minutes. We are also going to be seeing time in hours, or we're also going to be seeing time in days. Now, for the temperature, the unit of temperature, the SI unit, is Kelvin. But we work with degree Fahrenheit, and we also work with degree Celsius. So when we get to conversion, we are going to see how we can convert between this system of units. We also have light intensity, which is the candela. We have the electric current, which is measured in amperes. And we have the amount of substance, which is measured in mole. So these are fundamental units. All the other units that we have, we call them derived units. So for the derived units, we have like the meters cube, which is a derived unit from the length. We are talking about volume here. We have velocity, which is meters per second, which is the relationship between the length and the time. We also have density, which is kilograms per meters cube, which is using the mass and the volume. So these are called derived units. Now let's look at metric prefixes. For metric prefixes, we are looking at, if you see, for example, mega, what does mega stand for? If you see kilo, if you see deci, what do they stand for? Now, let's start with the positive. So let's start here at 0 at this point. Now, if we have kilo, a kilo means it is 10 raised to the power 3, which is 1,000. If you see mega, it is that unit times 10 raised to the power 6. If you see giga, it is that unit times 10 raised to the power 9. And if you see tera, it is times 10 to the 12. Now, when you see decimeters, for example, it is that unit, is that value that you are given times 10 raised to the power minus 1. When you see centi, 10 times that unit times 10 to the minus 2. When you see milli, times 10 to the minus 3. Micro times 10 to the minus 6. Nano times 10 to the minus 9. And pico times 10 raised to the power minus 12. And you need to know all of these prefixes because you will be given questions where you have to convert all of this. Now, for example, here, if you have 160 million bits, okay, 160 million bits is the same like if we have to convert that using any prefix here. For example, if you want to use mega, that is going to give us 160 megabits. Okay, So if we have 0.000032 grams and we have to convert it using one of these prefixes here, for example, the micrograms, that's going to be like 3.2 times 10 raised to the power minus 6. That is micro. So you need to know how to use all of these prefixes. So that is what it is. Now, let's see how we can use common metric prefixes. For example here, how many meters are in a kilometer? So you need to understand this table here. So when you see kilo, you know that it is 10 raised to the power 3. So how many meters are in a kilometer? It is going to be 1 kilometer is equal to 1,000 meters. How many amperes are in a mega ampere? So it is going to be 1 million. That is 10 raised to the power 6. So how many milligrams are in a gram? So if you are moving from gram to milligrams, how many milligrams are in a gram? You are going to have more of the milligram. So that is 10 raised to the power negative 3. So that is how you convert. So you have all of these conversions and you need to know them. So mega is capital M, which is a symbol, and the meaning is 10 raised to the power 6. Kilo, small k, lowercase k, which is 10 raised to the power 3, and milli is 10 raised to the power minus 3. Now, let's see how we can describe the quality of a measurement in chemistry. So we carry out measurements all the time because we have to be precise. Let's see how we can describe the quality of a measurement. So the quality of a measurement can be described using what we call precision and accuracy. And when we talk of accuracy, what do we mean? And when we talk of precision, what do we mean? So accuracy refers to how reliable the measurements are. When we say a measurement, something that we have measured is accurate, it means that they are very close. It reflects the true value. Okay, so with accuracy, we are looking at the value that we've carried out. How close is it to the true value? So that is what is referred to accuracy. Now, when we talk of precision, we mean how finely are the measurements made. That means how close are the measurements to each other. Let's say we had 5 measurements. If those measurements are close to each other, for example, one is 1.1, the other one is 1.1, the other one is 1.2, the other one is 1.3. If they are close to each other, then we say the measurement is precise. Now, if those measurements we've carried out are close to the true value, we say the measurement is accurate. So that is what we are looking at. Now let's look at precision and accuracy in terms of a target here. So you have a target and you have to fire the target. For example, the bullseye. Here, in the first case, we have fired the shots at the target. So, is this precise and accurate, or is it precise and not accurate, or is it precise and accurate? So, this one we have fired at the target, which means that all our shots went to where we expected and they are really close together, which means that it is accurate and it is precise. So that is the first case. In the second case, we have fired shots and we see that those shots are close to each other. Okay, so those shots are close to each other, but they are not close to the target. The target is right here. So they are close to each other, but they are not close to the target. So this, we can say it is precise, but it is not accurate because it didn't hit the target. Now let's look at the third case here. In this third case, we are firing shots just randomly anyhow. So we see that though they are not close to each other, they are accurate because the average they are falling around the same area. So this is accurate but not precise. It is not precise because they are not close to each other. So this is accurate but not precise. Now let's look at the last case. The last case here, the shots are just fired at random. They are not together, they are not close to each other, and they are not hitting the target. So the last case here, they are not accurate and they are not precise. Now let's look at it in terms of measurement. Let's look at the significant digits in terms of measurement. For example, here we have a beaker and we have a graduated cylinder. If you are asked to read the volume here in the beaker, so we see that between 20 and 40, we have one graduation, which means that that is 30. So the graduation here is 30. So the difference is 10. So we move from 20 to 30 to 40. Then from 40 to 50, then 60. Then 60, 70, here 80, 80, 90, here 100. So if you are asked to read this volume out, so you will see that it is above 40. So you already know for sure that it is 40 something. Now, it is close to 50, but not touching 50. So it's around 48 or 49. So we are looking at two significant figures here. We are looking at 48. So it could be 48 milliliters. It could be 49 milliliters. Now, if we look at the graduated cylinder, at this point, we are looking at the lower meniscus here, the lower meniscus. So we see between the graduations. For example, if we move from 0 to 10, or from 10 to 20, we have 10 graduations between 10 here to 20. Between 10 and 20, we have 10 graduations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each graduation is a milliliter. Now, if you have to read out this volume here, between 40 and 50, it's going to be at position. We have 40, 41, 42, 43, 44, 45, 46, 47. So you see that it is not directly on 47. It seems to be a little bit above 47. So you could say it's 47.1 milliliter. So in any of these cases, for the first example here, we have two significant figures. That is, we are looking at the accuracy, and every measurement that we make, the measurement cannot be more accurate than the measuring apparatus that we are using. So this case, for the beaker, we have 2 sig figs here, and here we have 3 sig figs. So that is how we can do the estimate. So the significant digits here, they indicate how precise we know a measurement, and the measurement cannot be more precise than the apparatus that we use. So here, if you say it's 47.10, that is wrong. And here for 48, you cannot say it's 48.1, that is wrong. So you have to take into consideration the apparatus that you are using. So these 2 significant figures, and this is 3 significant figures. Now, the graduated cylinder is more precise than the beaker because it gives us 3 significant figures. Now, let's see how we can identify significant digits in a calculation or in a measurement. So when you carry out a measurement, you may have 0.000010 or whatever value you may have. How do you know which digits are significant or which digits are not significant? So let's look at zeros. Now we are going to be looking at about 4 cases. Zeros that are we are looking at non-zero numbers. We'll be looking at sandwich zeros. We'll be looking at trailing zeros. I'll be looking at zeros before a decimal. Now let's look at the first case. All non-zero digits are significant, and all zeros between non-zero digits are significant. So we call this sandwich zeros. So all sandwich zeros are significant. All non-zero digits are significant. So that is rule number 1 for identifying significant digits. Now, we have 5 significant digits here in this first measurement. And for the second measurement, we also have 5 significant digits. The 0 is significant. Now, let's look at the second case. If a decimal point is present, zeros to the right of the last non-zero digit are significant. So here, because there is a decimal point, these 2 zeros are significant. So in this measurement, we have 3 significant digits. Here in this other example here, this 0 is also significant as well. So we have 3 significant digits. Now for 4.99, everything is significant. We have 3 significant digits. So the zeros are significant. Or what we have here, 3 significant digits in all of these measurements. Now let's look at the third case. Sorry, zeros to the left of the non-zero numbers are never significant. Okay, for example, we have 0.0000012 kilograms. So we have just 2 significant numbers here. And also here we have 0.0045, just 2 significant digits. So any 0 that is coming before a non-zero number, it is not significant. So all these 4 zeros are not significant. We have just 2 significant digits. These 2 zeros here are not significant. We have just 2 significant digits, which is 45. So how many significant digits are in 4.5 millimeters? You can pause the video and you answer the question. So there are 2 significant digits. Now, how many significant digits are in 0.0045? So we have 2 significant digits. The zeros are not significant. Now, they are just placed there as placeholders for the decimal. So that is the function of the zeros there. Now let's look at the fourth case here. If there is no decimal point present, zeros to the right of the last non-zero may or may not be significant. Let's look at this first case here. We have 10 million, sorry. So we have $10 million. So are all these zeros significant or not significant? So we have said they may be significant or they may not, because you may be estimating this 10 million that it is between 9 million and 11 million. So in that case, we cannot say for sure if the estimate that you are using is like 100, like if you are using 1,000, sorry, that is 10,000, 10 million, 100, 10 million. If you have like 10 million and 1,000, so you will have the 3 digits here. These 3 non-zeros, these 3 zeros here will be non-significant. So if you have like 9,999,000, you will have these zeros here. They will not be significant. Now let's look at how we can define significant digits for large numbers. For example, here we have 10,000 kilograms. So are these zeros significant or not significant? Like we've said, they may or they may not, based on how we define them. Now, if we are doing our measurements, like we have to bring out an uncertainty. The uncertainty here is like plus or minus 100 kilograms. So it means that the three first zeros here, the 3 2 zeros here, they'll be significant if you are looking at plus or minus 100 kilograms. So that is the first way of expressing it. We can also use the scientific notation, which is the second way of expressing it. So if we have to have 3 significant figures from 10,000 and we are asked to express it in 3 significant figures, we are going to have 1.00 times 10 to the 4. Okay, so this is 3 significant figures. All these zeros here coming after the decimal place are significant. Now let's look at a summary of significant digits. We've said significant digits show the precision of a measured quantity. Whatever we are measuring, we are looking at the precision. The accuracy is the true value. So every measurement that we do is just always about precision. Now, which zeros are significant? All non-zero numbers are significant. Sandwiched zeros, those are zeros between non-zeros that are significant. Zeros after decimal point, they are all significant. And which of them are not significant? The zeros to the left of all non-zero numbers, they are not significant. And the zeros, the trailing zeros, they may be significant or not significant. So depends on how we define them. Now let's look at what we call exact numbers. For exact numbers, we are going to see two classes of exact numbers. And the first class of exact numbers are counted values. First of all, what are exact numbers? These are values for which there is no uncertainty. So for counted values, there is no uncertainty. For example, if you are given pennies, so here, and you are asked to count these pennies, here we have exactly 7 pennies, okay? So we've counted them. This is 1, 2, 3, 4, 5, 6, 7. So there is no uncertainty in this counting. So those are exact numbers. And exact numbers, they do not limit the number of significant figures in our calculations. So that is the first class of exact numbers. We've said they are counted values. The second class of exact numbers are defined values. On what are defined values? For example, we say a kilogram is 1,000 grams. Okay, 1,000 milligrams is equal to 1 gram. We said a kilometer is equal to 0.639 miles or whatever. So those are exact numbers and they are defined. So you don't measure them. It's not based on measurement. So they are exact numbers. So they do not limit the number of significant figures in our calculations. Shortly, I will be showing you how we can use significant, exact or non-exact numbers to calculate, and you will see that the exact numbers are not limiting our calculations. So let's look at calculations with significant digits. For example, if you are asked to calculate the diameter of this ball, we have a ball here and you're asked to measure the diameter. Here is a ruler. You have been given a ruler here and you're asked to measure the diameter. So the first thing that you see is that there is a certain digit that you know. There is a certain digit and the certain digit here is 2. So you have 2. So any other thing is you could have 2.6, you could have 2.7, you could have 2.8. So all of those numbers, they are numbers that have uncertainty. So the 0.6 here, the 0.7, and the 0.8, those are uncertain digits. So the certain one is 2. So the 0.6, 0.7, 0.8, they are uncertain. Now, let's say we are going to work with the 2.7, which is like in the middle. And we choose the 2.7 because it's the one in the middle, and we move ahead and see how we're going to calculate. Now, for example, what is the circumference of the ball? So to measure the circumference using the diameter, we know that the circumference is equal to pi times the diameter. Pi is equal to 22 on 7, or 3.14. So if you want to measure the circumference, you are going to take pi times the diameter. Now let's see how we can calculate the diameter. So how we can calculate the circumference using the diameter that we had. So when we measure the diameter, we said it was either 2.6, 2.7, or 2.8. And we decided that we are going to work with 2.7 centimeters. Now let's use all those estimated values that we used and see what we are going to obtain. So if we use 2.7 and multiply by pi, the value that we are going to have here is going to be 8.45230016 centimeters. Now, if we use 2.6 centimeters or 2.8, now let's start with the 2.6. If we multiply the 2.6 by pi, we are going to obtain 8.1681490 centimeters. If we use 2.8, we're going to obtain 8.79645943 centimeters. Now, we already said that we were going to use 2.7 centimeters. So that is the accepted value that we used. And remember, a measurement cannot be more accurate than the measuring instrument that we are using. So we have to have just 2 significant digits in our answer. So we are using this case. So this is the answer that we obtained for the circumference. So we are supposed to have just 2 significant digits. So what are the significant digits that we are going to obtain here? We are not going to have just 8.4 because we are going to round up. So if we round up here, we are going to have 8.5. Shortly, I'll be showing you how to round up. So all of these will give us the answer here to be 8.5 centimeters. Now let's see how we can carry out division and multiplication of significant digits. So when we multiply or divide, we report the same number of digits as the least precise starting measurement. Now let's look at this example. A vehicle travels at 315.3 miles in the span of 5.2 hours. What is its average speed in miles per hour? So if you look at this 315.3, it has 4 significant digits. If we look at 5.2 here, it has 2 significant digits. So our final answer must have 2 significant digits. So that is the law of multiplication and division of significant digits. So the answer that we are going to obtain here must have 2 significant digits. So let's go ahead. So we are going to divide 315.3 miles by 5.2 hours. So what we are going to obtain is that the one that is limiting our calculation is the 5.2 because it has just 2 significant digits. The 315.3 has 4 significant digits. Here 2, and our final answer is going to give us 2. So whatever answer that we get, we are going to round it to 2 significant digits. So this is 60.63461538. Now, how do we round up or round down? That is called rounding off. If you want to round up a value or round down, if the value is more than 5, you round it up and you add to the preceding value. For example, in this case, 6 here is more than 5. So we are going to round it up to 1 and add to 0. So this calculation is going to give us 61 because we can have only 2 significant digits. So this is going to be 61. Okay, let's say that is the final answer that we had. Let's say we had something like 60.43210, whatever. Now, if we had that value, our final answer would have been 60 because this is not up to 5, so we round it down. So the final answer would have just been 60. But in this case, that is how we round up or we round down. Now let's look at addition and subtraction. For multiplication and division, we are looking at the least number of significant digits. For addition and subtraction, we are going to see that we are looking at the number of decimal places. So when we are adding or subtracting, we round to the last decimal place of the least precise starting measurement. Now see, in this example, while training for a triathlon, you swim 0.432 miles, then bike 18.1 miles. What was your total distance traveled? Now, we see that for swimming, you had 0.432 miles. You have 3 decimal places here. And for the biking, you had 1 decimal place. So your final answer is going to contain 1 decimal place. So there is only going to be 1 decimal place in your final answer. So let's go ahead and see. So we add the 2 together. What do we obtain? We obtain 15.532. So our answer is supposed to have just 1 decimal place. So how do we do that? Because the 1 decimal place is the one that is limiting. So our answer, our final answer is going to be 18.5 because 3 here is not up to 5. If it was up to 5, we would have rounded up. Okay, so our final answer here is going to give us just 15.5. We've rounded down every other thing. Now, so those are the rules for multiplication and division, then addition and subtraction. Remember, for multiplication and division, you choose the number with the least number of significant digits. Then for addition and subtraction, you choose the number with the least number of decimal places. So looking at rounding calculations with significant digits. So if a calculation involves multiple steps, you have to wait until you get to the end before you round to the significant digits. Now, let's look at an example here. A chemist measures the mass of chloride in 3 water samples as shown in the table. Together, the 3 samples have a volume of 2.31 liters. What is the average mass of chloride per liter of water? Answer to significant digits. Now, what are we going to do in this case? We are going to calculate the average mass, okay? Because we've been asked the average mass per liter. So we are going to calculate the average mass and we divide by the 2.3. So we are going to add the masses and we divide by 2.31 liters. So let's go ahead and do the addition of the masses. So we are going to have the total mass over the volume. So let's add the masses together. So we have 15.21, 9.33, and 11.329. That is going to give us 35.869 milligrams. So that is what we have. We've added. Remember, we've said that when we are adding, the number of significant digits is limited by the one that has the least number of decimal places. So here we are looking at this point. So that is where we are. So that would be like 35.87 because 9 here is greater than 5. We add it. But remember, we have to keep everything true until we get to the end before we round up. So we are going to be using in our calculation. We know that what is limited is actually 35.87. But in the calculation that we are going to divide the total mass by the volume, we are going to divide 35.869 and not 35.87. We cannot round up at this point. We only round up when we are at the end of our calculation. So this is 4 significant digits, but we are going to be using everything that we have. Now, we are using the unrounded mass, which is 35.869 divided by the 2.31 liters. That gives us 15.52770563. Now in this division here, what is limiting our number of significant digits is 2.31. So it has 3 significant digits. Remember? So our final answer is going to be 15.5. The one up has 4 significant digits. Why does it have 4 and not 5? Because we took it from this point. From this point, it was just 4 significant digits. So that is why here we talk of 4 significant digits and not 5. This 9 is still there, but we don't consider it. The one at the bottom has 3 significant digits. So our final answer must have 3 significant digits. So that gives us 15.5 milligrams per liter. Now, we've looked at all of these things. Now, we are getting into the last part of this lecture, which is unit conversions. How can you convert from one system of units to the other? Let's say, for example, here in US, we buy gas in dollars per gallon. So if you are moving from US to, say, you're going to UK, where you will have to buy gas in pounds per liter, how do you do that conversion? Or for example, here, we measure the distance that we travel in miles, and you are getting somewhere where the distance is measured in kilometers. So how do you convert the miles to kilometers? That is what we are going to be looking at this last part of this lecture, which is called unit conversions. And for unit conversions, we are using the system called dimensional analysis. Very important. And we'll be looking at conversion factors here. So whatever we do to the number, we also do to the units. Okay, that is what we'll be doing. So let me show you an example of what I'm talking about. Here we are measuring the area of this plot. Let's call it a plot, a piece of land or whatever. We are measuring the area, and we know that the area of a square is side times side. So here each side is 10 feet. So if we want to measure the area, we are going to have 10 feet times 10 feet. Okay, so that gives us, we have said whatever we do to the number, we also do to the unit. This is the unit. So whatever we do to the number, we also do to the unit. So we have 10 times 10, we are going to have 100. And we also do it to the unit. Feet times feet, that gives us feet square. So that is going to give us 100 feet square, or square feet. So that is what I mean by whatever you do to the number, you also do to the units. So that is it. Now, let's say you are using a micropipette here and you have to measure the amount of toxin in a milliliter of something. So the conversion factor is that the amount of toxin in a milliliter of blood. Let's say for example, we are using blood. The amount of toxin in a milliliter of blood is 1.02 milligrams. How many milligrams of toxin will be in 15.0 milliliters of blood? So this is called the conversion factor. In 1 milliliter of blood, we have 1.02 milligrams of toxin. So how many milligrams of toxin are we going to have in 15.0 milliliters? So we arrange this in a way that the milliliters is going to cancel out. So this conversion factor that I've circled here, you could reverse it and put the 1.02 at the bottom. You just arrange it such that the units that you don't want cancel out, and the ones that you want, they actually stay. So if you do that, you see that you are going to have 15.3. The milliliters will cancel with the milliliters, and you are left with units of milligrams. Now, let's look at a second example here. A copper pellet has a mass of 0.281 kilograms. What is this mass in grams? So we are converting from kilograms to grams, and what we are going to be using here is the conversion factor. And the conversion factor is that 1 kilogram is equivalent to 1,000 grams. So as we already know that 1 kilogram is equivalent to 1,000 grams, that is what we are going to use. So 1 kilogram is equal to 1,000 grams, or 1,000 grams is equal to 1 kilogram. So you see these two conversion factors here, all of them are the same. You just have to arrange them such that the units that you don't want will cancel out. So for us to solve this problem, we start by writing out the mass that we've been given. And what's the mass that we've been given? 0.281 kilograms. So we have to arrange it such that the kilogram will cancel. So here we have the kilogram at the top. So which conversion factor are we going to use? This one, let's call it A or B. So pause the video and decide if we are going to use the conversion factor A or conversion factor B. Alright, now we are going to use the conversion factor B because the kilograms at the top is going to cancel out with the kilograms at the bottom, and we are left with grams. So that is what we are going to use, 1,000 grams over 1 kilogram. So the kilogram cancels out and we are left with grams, and that gives us a value of 281 grams. So that is how we use dimensional analysis to convert from one system of units to the other. So these are the starting units, the conversion factor, and the ending unit in grams. Now let's look at this other example. How many inches are in 326 centimeters? So you are given centimeters and you have to move from centimeters to inches. Now the very first thing that you have to know is the conversion factor. What is the conversion factor between inches and centimeters? 2.54 centimeters is equal to 1 inch. Now let's write out our conversion factors. So the starting unit is in centimeters. The conversion factor here is 1 inch is equal to 2.54 centimeters, or 2.54 centimeters is equal to 1 inch. So what I'm saying is you can write it this way: 2.54 centimeters is equal to 1 inch. Or you could also write it this way: 1 inch is equal to 2.54 centimeters. So based on what we are given 326 centimeters. So let's say this is A and this is B. Which of the conversion factors are we going to use? A or B? You can pause and you answer. Alright, so in this case, the conversion factor that we are going to use is B, because the centimeters is at the bottom and the centimeters will cancel out and we are left with inches. That gives us the ending unit. So we are starting with centimeters, the conversion factor, and the ending is inches. So we have 2.54 centimeters per inch or that. So that is exactly what we are going to do. We are going to use this one because the centimeters is going to cancel out. So we have 326 centimeters times the conversion factor. 1 inch is equivalent to 2.54 centimeters. And the centimeters are going to cancel out and the ending unit is going to be in inches. And what is that value? 128 inches. So that is how you do it. Now, what happens if you do the reverse? Instead of using the 1 inch equivalent to 254 centimeters, if you invert it, what are you going to obtain? You see that here, nothing will cancel out, and you will instead have centimeters square over inches, which is not what we've been asked, and you have the wrong answer. So you have 828 centimeters square per inch, which is wrong. Now, let's look at this other example. The speed of light in a vacuum is 3.00 times 10 to the 8 meters per second. What is this speed in miles per hour? Now, the conversion factor here is 1 mile is equivalent to 1,609.3 meters. And for time, 1 hour is equivalent to 3,600 seconds. So to know that 1 hour is equivalent to 3,600 seconds, you say 1 hour is equal to 60 minutes. 60 minutes is equal to 60 seconds is equal to 1 minute. So if you convert that, you are going to have 3,600 seconds. So these are the values that we are going to use. So let's see how we are moving from meters per second to miles per hour. Okay, so we have two conversion factors here. Now, let's start with what we've been given. 3.00 times 10 to the 8 meters per second. So we have to arrange the miles per hour here. So we have been asked what is the speed in miles per hour. So this is our ending unit that we need. Now, with what we've been given here, we know that we have to use the conversion factor. Let's start with any of them, the meters to miles. So what are we going to do? So we have 1 mile is equivalent to 1,609.3 meters. So that what? So that the meters are going to cancel out. Okay. So if you reverse this, you're going to have the wrong answer. Now let's look at time. We want it per hour. So we have to arrange it in a way that the seconds are going to cancel out. And if we want the seconds to cancel out, here the seconds are at the bottom. It means that in our conversion factor, the seconds must be at the top so that they cancel out. So for the seconds, we are going to have the seconds at the top and the hours at the bottom so that the seconds cancel out with the seconds, and we are left with our conversion here now in miles per hour, which is what we've been asked in this question. So that gives us 6.71 times 10 to the 8 miles per hour. All right, so let's see how we can move to volume, units of volume here. After looking at units of volume, we will be looking at density. Now, if you are given a box and you're asked to calculate the volume will be given by side times side times side. So it's given by V cube, the A cube. So we see that each side is 10 centimeters. Remember, we've said we multiply the number and we also multiply the unit. So that is going to give us 1,000 cubic centimeters for the volume. Now, if we are looking at the volume that the unit of volume that we'll be using, it depends on the size that we are talking about. So if we are talking about the shipping containers, we are going to be talking about meters cube. If we are talking about a drink, we are going to be talking about decimeter cube. And if we are talking about a syringe or an injection, we are going to be talking about centimeters cube. Now, let's look at the volume sizes as they continue. Now, 1 liter is equivalent to 1 decimeter cube. Okay, you need to know this. And 1 milliliter is equivalent to 1 cm cube. So 1 liter is the same like 1 decimeter, and 1 milliliter is the same as 1 cubic meter. Now, let's look at cubic decimeters and cubic meters. How many cubic decimeters are in 1 cubic meter? So we are going to see, first we start by writing out our 1 meter, which is equivalent to 10 decimeters. This is our conversion factor. Remember, I told you that you must know those prefixes. That is exactly what we are using here. So 1 meter is equivalent to 10 decimeters. Now we are moving from 1 cubic meter to cubic decimeters. Whatever we do, if we cube the meters, we are also going to cube the decimeters. So we are cubing 1 meter here, and we are also cubing 10 decimeters. So 1 cubic meter is equivalent to 1000 decimeters cubed. Now, how many cubic centimeters are in 1 cubic meter? So we have to look at the conversion factor between centimeters and meters. We know that 100 centimeters is equal to 1 meter. Now, if we have to cube the meters, we also have to cube the centimeters. So when we cube that, we are going to have 100 times 100 times 100. So that is the meaning of cube. Don't get confused here. So that is going to give us 1 million. So 1 cubic meter is equal to 1 million cubic centimeters. Now let's look at how we can multiply unit conversions. For example, a hospital administrator, a hospital administers an IV fluid at a rate of 95.0 centimeters cubed per hour. How many liters of this fluid does the patient receive per day? Now, this is per hour. How many are they going to receive per day? We need the conversion factors here. So the volume and the time is what we are talking about. So the volume is 95.0 centimeters and the time is per hour. So we need it in liters per day. So we need to know how many hours in a day, and we need to know how many liters in a centimeter, right? So those are very important units. So we know that 1 centimeter cube is equal to 1 milliliter, and we know that 1000 milliliters is equal to 1 liter. So 1000 centimeters cube is equal to 1 liter. So that is the conversion for the volume. What about time? We know that 24 hours is 1 day, and we are going to look at the value that we've been given here in our units of cubic centimeters per hour, and we use the conversion factor. Our final answer is to be in liters per day. Okay, so here the conversion factor that we are using here in terms of centimeters and liter, this is what we are going to use. Now, is the cubic centimeter going to be at the top or at the bottom? You can pause and answer that question. So the cubic centimeter is going to be at the bottom so that you can cancel out with the cubic centimeter here. So that is what we have, the liters at the top, the cubic centimeters at the bottom. Now, we have the hours here at the bottom, and our answer is supposed to be in per day. So this is the conversion factor that we are using for the time. So are the hours going to be at the top or at the bottom? You can pause the volume, the video, and you check it out. So the hours are going to be at the top so that they can cancel out with the hours here at the bottom. So our conversion factor, cubic centimeters, have cancelled out here. Now for the hours, we'll see that the hours is going to be at the top and the days at the bottom. So the hours will cancel with the hours, and we have our unit in liters per day. So if you multiply that out and you divide, the answer that you will arrive at is 2.28 liters a day. Now let's see how we can relate mass and volume. So we just saw how we can calculate the volume of a box here. So we have the mass, how we can measure the mass using the balance, how we can measure the volume using the graduated cylinder. So there is that relationship between mass and volume, which is density. Okay, so density is given by mass over the volume. Now, if you have the density and the mass, you can calculate the volume. If you have the volume and the mass, you can calculate the density. So you can use any of these to get any of the factors. One, if you have two, you can get the other one. So D is equal to M over V, where D is density, M is mass, and V is volume. So let's look at an example of density. Now, for density, if something can sink or it can float, we are looking at it in terms of density. Like for example, you see this person here floating on the water. It means that the density of that apparatus is less than the density of water. That is why he is floating. Now, if you take something like a stone and you throw it into that water, it's going to sink. The stone sinks because the density of the stone is higher than the density of the water. Let's do this example. A saltwater solution has a mass of 11.29 grams and a volume of 10.4 milliliters. What is the density of this solution? Now, we know that density is equal to mass over volume. We've been given the mass to be 11.29 grams and we've been given the volume to be 10.4 milliliters. So we simply divide 11.29 divided by 10.4. That gives us 1.09 grams per milliliter. Remember, units are very important. You must always state your units. Example 2. An antifreeze mixture has a density of 1.06 grams per milliliter. If you measure out 600.0 grams of this solution, what volume will it occupy? So we first of all start by stating the formula of density, which is mass over volume. Now we've been asked to calculate the volume. We are given the density and we are given the mass. So what is the volume? Volume will be given by mass divided by density. Okay, so we go ahead, we divide our mass, which is 600.0 milligrams divided by 1.06 gram per milliliter. We see that grams will cancel with grams and our volume would be in milliliters. So that gives us a value of 566 milliliters. Now, here, let's look at an aluminum has a density of 2.70 grams per cm cube. What is the mass of a block of aluminum with a volume of 1.32 liters? So here we have the density, we have the volume, and we are looking for mass. So we start by stating the formula of density. Density is equal to mass over volume. If we are looking for mass, mass will be equal to density times volume. Okay, so we simply multiply the density and the volume. And before we do that multiplication, look at the units. The volume here has been given in liters, but the units of density are in grams per centimeter cube. So we must convert the liters to centimeters cube. And remember how to do that conversion. 1 centimeter cube is equal to 1 milliliter, and 1000 milliliters is equal to 1 liter. So we are going to convert 1.32 liters to centimeters cube. And for us to do that, we are going to multiply by 1000. And that gives us 1320 centimeter cube. So our conversion factor here is 1000 centimeters cube is equal to 1 liter. And our value is 1.32 liters. So liters in the conversion factor is going to be at the bottom so that it cancels out with the liters at the top. So we have 1320 cm cube. We are just going to multiply that by 2.70. So the centimeters cancels out with the centimeters, and we have our mass in grams, which gives us 3.560 grams. Now let's look at the common densities, the density of common materials here. So we are going to look at the density of water. The density of water is very important. So we are going to be comparing the other densities with the density of water. So all these materials here, aluminum has a density of 2.70, titanium has a density of 4.51. No need to cram, but you should know the density of water. The density of water is 1 gram per cm cube. So if you are given anything that you have to do these calculations, the densities will be given to you. Now, we have water here with a density of 1.0 gram per milliliter, and we will be given a block of wood and a block of aluminum. So which one is going to sink and which one is going to stay at the top, and why? So we see here that the block of wood with a density of 0.4 grams per milliliter is less dense than water, which has a density of 1. And for the aluminum is going to sink because it has a density of 2.7 grams per milliliter. So it sinks because it has a higher density. Now, let's look at this calculation. A rectangular object measures 3.0 centimeters times 2.0 times 1 and has a mass of 7.2 grams. What is the density of this object? Will it float in water or will it sink? Now, density, as we know, is mass over volume. Here we've been given the mass, 7.2 grams. We've not been given the volume. From these values that we've been given from the rectangular object, we can calculate the volume. So the volume will be gotten by 3 times 2 times 1. So that gives us the volume. The length times width times the height. That gives us 6 centimeters cube. That's the volume. And the mass is 7.2 grams. So the density is mass over volume, which is 7.2 grams over 6.0 cm cube. That gives us a value of 1.2 grams per cm cube. Now, will it float in water? Remember the density of water. Water has a density of 1 gram per cm cube. So we see here that the density is higher than the density of water. So it's going to sink. It will not float. Now, let's see how we can convert between temperatures. Now, in the US, in the United States of America, we use our temperatures in units of Fahrenheit. So other units of temperature are the Fahrenheit. We have the Fahrenheit, we have the Kelvin, and we have the degree Celsius. Now we are going to see how we can convert from any of these units to the other. Let's start with Fahrenheit and degree Celsius. So for the Fahrenheit, we know that the freezing point of water is 32 degrees Fahrenheit and the boiling point is 212 degrees Fahrenheit. For the absolute 0 point, the absolute 0 is minus 460 degrees Fahrenheit. Now for the Celsius scale, the absolute 0 is negative 273 degrees Celsius. The freezing point of water is 0 degrees Celsius. And the boiling point of water is 100 degrees Celsius. Now, if you want to look at between the freezing point and the boiling point, and you look at the range here for the degree Celsius and for the degree Fahrenheit, you will see that 212 minus 32 gives you 180 degrees Fahrenheit. So if you take 100 degrees Celsius minus 0 degrees Celsius, that gives you 100 degrees Celsius. So you see that 100 degrees Celsius is equal to 180 degrees Fahrenheit. So that is the main information that we are going to be using to convert from degrees Celsius to degree Fahrenheit. So equally, you could say that 1 degree Celsius is equal to 1.8 degree Fahrenheit. So that is the information that we get from here. Now, let's see how we can do these conversions now. So, moving from degree Celsius to degree Fahrenheit, you have to divide the degree Celsius by, you have to multiply it by 9/5, then you add 32. Why are you adding 32? Because at this point, you see that 0 degrees Celsius, you are already at 32 degrees Fahrenheit. Now, you could also write it this way, that degree Fahrenheit is equal to 1.8 degrees Celsius plus 32. That is the same thing. So 9, if you are somebody who is scared of fractions, you can use the decimal. So if you have to convert from degree Fahrenheit to degree Celsius, I'm just going to continue from here. If you want now to move to degree Celsius, you are going to see that degree Celsius is equal to degree Fahrenheit minus 32 over 1.8. That is the same thing like you have from degree Celsius here, it's 5 over 9 degrees Celsius minus 32. So that is the same thing. Whichever one is easier for you, you can use it. Now, if we have to convert between the 3 temperature scales, that is the degree Celsius, degree Fahrenheit, degree Kelvin, how are you going to do that? Now, we have already seen the Fahrenheit and the Celsius scale. Now we are looking at the Kelvin scale. For the Kelvin scale, 0 degrees Celsius is equivalent to 273 degrees Kelvin. Okay, and 100 degrees Celsius is equal to 373 Kelvin. So we see here that between 0 to 100 degrees Celsius, the same between 273 to 373 is 100 Kelvin. So a change of 1 degree Celsius is equal to a change of 1 Kelvin. So that is going to be easier for us to convert to degrees Celsius and Kelvin. One more thing that you have to remember is that at 0 degrees Celsius, we already have 273 Kelvin. So 0 degrees Celsius is equivalent to 273 Kelvin. So that is what we are going to use in our conversions. So if you have your temperature in degrees Celsius and you have to convert to Kelvin, you just add 273. So if you have it in Kelvin and you have to convert to degrees Celsius, you just subtract 273. So that is how we are going to be doing it. So degrees, we have 32 degrees Fahrenheit here at this point. 32 degrees Fahrenheit is equivalent to 0 degrees Celsius, which is equivalent to 273 Kelvin. Now let's look at an example. A refrigerator maintains an inside temperature of 42 degrees Fahrenheit. Express this temperature in Celsius and Kelvin. So we've seen how to convert from degree Fahrenheit to degree Celsius, and we've also seen how to convert from Celsius to Kelvins. So the best way for you to do it, you cannot just convert from Fahrenheit to Kelvins. The best way for you to do it is to convert from Fahrenheit to Celsius, then from Celsius to Kelvin. Now, to convert from Fahrenheit to Celsius, remember it is 5 over 9 degrees Fahrenheit minus 32, or you could say it is degree Fahrenheit minus 32 over 1.8. That's the same thing. So this is degrees Celsius. So that is the same thing. And if you carry out that calculation, you're going to see that the temperature in degree Fahrenheit is 42. So you subtract 32 from it, multiply by 5, and then divide by 9. So that gives you a value of 5.6. So if you were to use this formula here, you would have said it's 42 minus 32 all over 1.8. 42 minus 32 divided by 1.8. So that is going to give you the same 5.6. So use whichever formula is easier for you. Now we've had the temperature in degrees Celsius. Now let's convert from degrees Celsius to degree Fahrenheit to degree Kelvins, not degree Kelvins. So we have degrees Celsius, we have degrees Fahrenheit, and we have Kelvins. So you cannot say 23 degree Kelvin. You just say 23 Kelvins. We said 23 degrees Celsius, 23 degrees Fahrenheit, and 23 Kelvins. So let's convert now our 5.6 degrees Celsius to Kelvins. So we know that from degrees Celsius to Kelvins, you just need to add 273.15. So if you do that addition, that is going to give you 278.75 Kelvin. So when we are adding, remember the rule of significant figures. We have just one decimal place here. The one decimal place is what is going to limit our decimal places in our final answer. So our final answer is supposed to have just one decimal place. That is why we have rounded up here to have 8. So the answer is 278.8.